In this next section, we're going to take a look at how to model matter. And what I mean by that is we're going to create a system where we can imagine matter at this very, very tiny microscopic level. So what we're going to do is we're going to describe this model, and that is that matter is made up of tiny particles smaller than we can see. And these particles are called molecules and atoms. And so these are two key words that we're going to go over today, molecules and atoms, and the difference between the two. But let's start out with atoms first. So an atom is defined as particles that make up molecules. So it's the smallest possible thing. The way I like to describe atoms to my students is these are the individual Lego building blocks that make up all matter, where a molecule is two or more atoms that are attached together via chemical bonds. So let's make a note, two or more atoms that are held together through a chemical bond. In addition, molecules are generally considered to be neutral, meaning they don't carry a charge with them. But we're going to talk more about charges later. We haven't really gotten far enough yet. And between molecules, we can further branch them down more. So what we'll do next is we'll look at diatomic molecules versus triatomic molecules. Versus polyatomic molecules. And as you can probably imagine, a diatomic molecule is a molecule that is made up of two atoms. That's what the prefix di stands for. Triatomic has three atoms. And polyatomic has more than three. So when we're looking at molecules, we can describe them even further into one of these distinct categories, depending on the number of atoms that make up that given molecule. So when you hear somebody talking about oxygen, for example, oxygen is O2, meaning two oxygen atoms are bonded together. From that, we can tell, hey, oxygen must be a diatomic molecule because it's made up of two oxygen atoms that are bonded together. In addition, we can further subdivide these into hetero and homoatomic. So heteroatomic molecule, and then homoatomic. And as you can probably tell by their prefixes, a heteroatomic molecule is made up of different atoms. So for example, if you have heard about carbon dioxide, that's made up of carbon and oxygen being different atoms. It must be a heteroatomic molecule, where O2, oxygen, is made up of two oxygen atoms that are entirely the same. So these are homoatomic. So we can really get down into the nitty-gritty of what type of molecules we're talking about by using either these terms, di, tri, or poly, in addition to hetero or homoatomic. Oftentimes we'll also use the term compound. We'll talk more about the difference between a molecule and a compound in a little bit. But what I want to do next is I want to jump into how we classify matter even further. So when we classify matter, we can first break it up into two main chunks. So what I'm going to do is make a little flowchart here. So I'll put matter on the top. And like I said, matter could be made up of either atoms or molecules. And if we have a sample, the sample of matter could either be pure or it could be a mixture. So let's kind of make a little chart here. So in matter, this could be made up of atoms or molecules. And if we have a sample of matter, that can be broken up into a pure sample or a mixture. All right, a pure sample, if we look at it, is made up of only one substance. And because it's made of only one substance, it will always have the same properties. And that is both chemical and physical properties, where a mixture is going to be made up of multiple substances. As you can tell by the name, it's going to be a mixture of multiple substances. Meaning maybe you've got two different types of molecules that are mixing together, or some molecules and atoms mixing together, where over on this pure side, we would only have one type of atom in there, or one type of molecule in there. So that's the main difference. And when we're looking at a mixture, the properties can differ depending on the composition, right? So if we think about, for example, mixing sugar and water, depending on how much sugar you add, that water is definitely going to have a different flavor, right? Meaning it's going to have a different property. So the composition of the mixture can change a lot about the overall mixture and the properties that that mixture has. All right, so we can further subdivide each of these. So in a pure sample, we can subdivide this into two groups. So I'll branch this. In the first group, we have what are called elements. And what elements are is it's a substance made up of only one atom type. So let's think about some examples of elements that we could have. So I used the example of oxygen, right? And oxygen, we said, is O2, but it's only made up of the element oxygen. Even though there are two of them, it's made up of only one atom, in this case being oxygen. We could also look at copper. Copper, if you look at it on the periodic table, has the elemental symbol Cu. So copper pipes, are made up of a bunch of copper atoms. So even though we could have a lot of copper or a little bit of copper, it's made up of only one atom type, so it would fall in this element category. All right, this is different from something called compounds, which I briefly mentioned before. And you can probably tell a compound is going to be made up of different types of atoms. More than one atom type. And a good way of thinking about this is if we look at something like water. Water is going to be H2O, which means we've got two hydrogen atoms and one oxygen atom. Therefore, the hydrogen is different than the oxygen. It must be a compound. Another good example would be methane. This is found in natural gas. This is CH4. So we've got one carbon atom along with four different hydrogen atoms. Another way you can clearly differentiate between these is elements are always going to be homoatomic, meaning they're going to be made up of one atom type, where compounds are always going to be heteroatomic. And I know one thing that used to confuse me was, well, what's the difference between a molecule and a compound? Well, if you remember, a molecule can be made up of atoms of the same type, but it has to be made up of more than one type of atom. So if we look at O2 over here, this would be an example of something that is a molecule, but is not a compound, right? Because it doesn't have two different types of atoms. So it is kind of nitty-gritty, but it's important to some degree. All right, so now let's go over and look at mixtures. All right, with mixtures, we can branch this into two different categories, just like we did with the other pure set. So the first branch that we're going to show is going to be homogeneous. And I remember taking chemistry and hearing that term, and I said, that sounds like the milk you buy in your grocery store, right? If you look at milk, it's called homogenized milk. So what does that mean? Well, it means that they've actually done something to the milk to prevent the fat from separating out. And what that means is that the fat is evenly mixed. And often, this is just called a solution. Whoops, let me fix this. Often called a solution. So a good example of this would be seawater. And if we think about what seawater is going to be made up of water, obviously. However, there's a lot of salt in there. And salt is made up of sodium chloride along with a bunch of other different things. But table salt is just sodium chloride. That's Na for sodium, and then Cl for chloride. So in this case, seawater is an even mixture of salt and water. We could separate these out if we wanted to, right? We could evaporate off the water and get the salt. We couldn't do any sort of separation of methane and break it into smaller pieces. Methane is just methane, right? So we would have to do a chemical reaction to break this up. Where this, we could actually just physically separate the water from the sodium chloride. So that's another big difference here. Right? The difference between these is the second mixture is called heterogeneous. And if we think about a heterogeneous mixture, it is something that is unevenly mixed. And if we think about some examples here, we could look at something like pizza, right? So pizza has crust, it's got cheese, it's got sauce, maybe a few other things on it, but they're not evenly mixed, right? There's layers, there's different chunks of maybe pepperoni. It's not evenly mixed. So this would be a good example of a heterogeneous mixture. Another one could be oil and water. Oil and water don't mix, they'll separate out, meaning even if you shake it, they'll separate out. There's no way of really getting these to mix well. So all of these would be good examples of a heterogeneous mixture. All right, so this is the main flowchart that I like to make with students to kind of show the difference between all of these different groups. But what I want to do next is just quickly test you. My question for you is, what about blood? What category would blood fall under? Would it be an element, a compound, a homogeneous mixture, or a heterogeneous mixture? Well, we could go through the flowchart and we could say, well, blood's definitely matter, right? It has mass and takes up volume. Then we could ask ourselves, is it pure or is it a mixture? I would say it's probably a mixture, right? Because we've got different cell types. We've got white blood cells, we've got red blood cells. We even have the liquid within our blood, which is called plasma, which is different than red blood cells. So I'd say it's definitely going to go down into this mixture category. And if we think about whether or not it's mixed evenly, the question is, how easy is it to separate these out? Well, I would say the cells are almost like these little itty-bitty boats floating through your blood. I would say they aren't perfectly mixed. They're somewhat unevenly mixed, and we can physically separate blood from plasma. So if you ever do plasma donations, you can isolate your plasma. So I would consider blood to be a heterogeneous mixture. It does kind of depend on the scale. If you look at it from the very macro scale, you could argue, well, maybe it's homogeneous, but I would argue that because we can physically separate out those blood cells from the plasma, we could consider it to be heterogeneous. All right, let's consider air though. What about the air in the room around us? Well, we know that the air in our room isn't pure oxygen. If it were, we would light a match and we'd all die. And that's a good thing that we don't have 100% oxygen in the air. In fact, the air around us is mostly nitrogen. It's like 70% nitrogen. I think it's about 20 some percent oxygen. And then the leftover stuff is a bunch of other gases. So in this case, we would look at it and we'd say, well, it's not an element, right? It's definitely a mixture of different compounds. So I would argue that it's probably going to be either homogeneous or heterogeneous. It's going to be a mixture of some sort. But in this case, it's evenly mixed. It's a lot harder to physically tweeze out molecules from other molecules, right? As opposed to blood cells, which we could physically separate. So over here, I would say the air is going to be a homogeneous mixture. All right, let's do one last one. Let's consider benzene. And benzene is a molecule with the formula C6H6. It's one of my favorite molecules because I'm an organic chemist. I love carbon. If we look at this, we could say, well, it's not a mixture. It's only one type of substance, right? And then we could ask ourselves, well, is this an element or a compound? Well, in this case, it's made up of both carbon and hydrogen atoms, so I would call this a compound. All right, I hope that makes sense, but let me know if you have any questions.